All right, we have finally made it to the last chapter, chapter 12, looking at section 12.1, chi-squared test for goodness of fit. Now you might be asking, what's a chi-squared? We will definitely take a look at it today. So some learning targets right now. You should be able to state the appropriate hypotheses and compute the expected counts and chi-squared test statistic for a chi-squared test of goodness of fit. State and check the random 10% and large count condition for performing a chi-squares test for goodness of fit. Calculate the degrees of freedom and p-val for a chi-squared test for goodness of fit. Perform a chi-squared test for goodness of fit and conduct a follow-up analysis when the results of a chi-squared test are statistically significant. So as you can see, a lot of stuff with this new thing called chi-squared. So let's take a look at it. Well, if you think back to all the testing that we've done in chapter 8, 9, 10, and 11, it was all just based on one sample with one variable we're looking at, and you're either looking for just of one population or maybe a difference of population, but it's just about the one variable. Okay. Um, in chi-squared, we can look at, there's a couple different ways we do testing, but one is looking at multiple categories. Okay, so for this example, here's what the Consumer Affairs Department of Mars Inc. said about the distribution of color for M&Ms, milk chocolate candies produced at its factory in New Jersey. So it says that brown is 12%, 12.5%, red is 12.5%, yellow is 12.5%, green is 12.5%, and orange and blue are both 25%. So before in chapter 8, 9, 10, or 11, you would only be able to do this to say what percentage of M&Ms are red or what percentage of M&Ms are blue. You wouldn't be able to test about all six different kinds. You would only be able to do about one specific category. So that's where chi-squaredness, that's why this problem is different than before. So Jerome's class wondered if the distribution of color in a large bag of M&M's milk chocolate candies differed from the claimed distribution. So here's the random sample of 60 that he took. So he found that 12 were brown, 3 were red, 7 were yellow, 9 were green, 9 were orange, and 20 were blue. So our hypothesis here, they're going to be a little bit different. They're typically used in words, or you could use them in mathematical symbols or equations, but look at them in words. So right now, the null hypothesis, what we assume to be true, is the distribution of color in the large bag of M&M's milk chocolate candy is the same as the claimed distribution. So that would mean that the alternative, in this case, is the distribution of colors in the large bag of M&M's milk chocolate candies is not the same as the claimed distribution. So with this chi-squared test, the hypothesis is always that it is what's claimed, and the alternative is it is not the same. Okay. So it will always, just going back, it will always be a two-tailed. It will always be not the same. Okay. So we can also write the hypothesis in symbols. So you could write whatever the given ones were, right? The probability of brown or the expected value of brown was 12.5%, red, yellow, and green were all 12.5%, and then orange and blue were 0.5. Then the alternative here is that at least two of the expected counts or expected probabilities are incorrect. Okay. And they say at least two. And this is a really important part. All six of them don't have to be incorrect. Okay. You really only need one probability to be wrong. But if one probability was wrong, then two would have to be wrong. What do I mean by that? Well, let's say we found out that P brown is really only 10%, not 12.5%. If it's only 10%, that other 2.5% has to be accounted somewhere. So what other category got that 2.5%? Then that would mean that that probability is no longer the same as it was before. So that's why it's always at least two of them are incorrect. You don't need all six or as many as the categories are there. You just need at least two of them. Okay. And that's what this big caution is. Don't state the alternative hypothesis in a way that suggests that all the proportions of hypothesized distributions are wrong, just that some of them are. in this case, two, at least two. The other thing I want to mention is that these tests will be very similar to how we would do a regular hypotheses testing, and you should see the similarities, and also we will highlight the differences as well. Um, but they should be very similar and should follow the same four-step process to an extent. Okay. So next subsection is comparing observed and expected counts, the chi-square test statistic. So how many candies of each color should Jerome's class expect to find in their sample of 60 candies? Well, if brown, red, and yellow really are 12.5%, if you had a sample of 60, you'd expect there to be about 7.5. And same thing for green. And then orange and blue are 25%, so there you'd expect to be 50. Notice the expected counts is very similar to um, the expected value calculation, right? It's just n times p. It's very similar, but it's just n times p. It's what we expect to happen would be if we had that probability out of this sample multiplied together, that's the expected count for this specific um, color or category in this case. All right. And I want to go back 1 second to emphasize something. In chi-square testing, looking at the alternative, the null and the alternative hypotheses, it's always that the distribution of colors in the large bag of M&Ms, so the distribution of colors in this sample is or is not the same as the claimed distribution. So when you do chi-squared, there's always going to be what you would expect. That's the claimed distribution, right? The expected values, and then in the large bag of samples, that's your sample or that's your um, sample values, right? Or your observed values, what you'd say. With a chi-square test, we're always going to have that observed number, and we're always going to have the expected. Like I said here, these are my expected numbers: 7.5, 7.5, 7.5, 7.5, and 15 and 15. And then here is our observed values. So we want to see how different these observed values are to the expected. Okay. And you can see here, we got observed in purple and red. And so theoretically, these should add up to 60 for both of them because that's how many are in this sample. Now the question is how are those 60 candies divided up? Also note that the observed values are just observed based on this one specific bag of 60 candies. If I took another sample of 60 M&Ms, they might be very different than this. Um, so it's just based on the observed test that you did or the sample that you have obtained. All right. And so the chi-square test really is this: how likely is it that differences this large or larger would occur just by chance in a random sample of size 60 from the population distribution claimed by Mars? So it's really how likely is it that these are different in a sample of 60? The statistic we use to make this comparison is called chi-squared test statistic. So it's pronounced chi-squared. That's how it's spelled. Or it's also this kind of fancy X with the squared number on it is the symbol for it. Think back to other test statistics we use were p hat or p or x bar. Well, p hat or x bar, right? They are test statistics that we're going to use. Here we are using our chi-squared. So how do you find chi-squared? Well, chi-square test statistic is a measure of how far the observed counts are from the expected counts. And this should be reinforcing that statement I made before of that chi-squared always has to have observed and an expected number. Well, in order to get the difference between these, you have to have both of those. So chi-squared will always have that observed and the expected counts. The formula for it is here. It may look very familiar to a standard deviation formula, but it's not the exact same. So it is observed count minus expected count squared divided by the expected count. And then you add those all up together. And you do that for each category. So you do this for red, for brown, for yellow, for green, for orange, for blue. You'd add them up, and that number is your chi-squared. Similar to like if you're finding your x bar, it's value plus value plus value plus value plus value divided by number of values. Same idea here, and then that number is your x bar. It is your sample mean. Here, whatever this number is our chi-squared value. So based on the values we found, we have that observed minus the expected. And notice how the expected is for the specific category. So don't fall into the trap where, oh, it's 7.5 for everything. The expected value is specific for that category. Okay? And that comes from whatever the population tells you. Here, Marsing told us that the expected value is this number or this percentage, so we can use it based on. So in this case, our chi-squared number is 9.8. And right now you might be like, okay, well, what does 9.8 mean? Is that good, bad? Where does it kind of fall? And we'll see how significant that value is, how significant our statistic is here um, in a little bit. We're going to look at one more example. Here's a problem. It says Carrie made a six-sided die in her ceramics class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcome of her 90 rolls. It says state the hypotheses that Carrie's would test. That's what part it is. Well, you would expect it. The sides of Carrie's dice are all equally likely to show up. That would be H naught. HA would be the sides of Carrie's dice are not equally likely to show up. And specifically, remember, we needed at least two of the values to not be the same. If you wanted to show this in number-wise, you could say the probability of rolling a 1 is equal to 1/6, 2 is equal to 1/6, and so forth. Because if there's six numbers, and it wants to say that they're equally likely to come up, that means that each one is going to come up 1/6 of the time. Since there's six outcomes. Number two, or sorry, B is calculate the expected count for each possible outcome. So expected counts would mean if HO is true, then the six-sided dice would show 1/6 of the time, like we said. The expected counts is for each number, it's the probability of that category times how many total trials there were. So there were 90 rolls here. The probability of getting a 1, we'd expect to be 1/6 because we expect this dice to be fair. So it would be 1/6 times 90 plus, sorry, that's for the first expected count. The expected count for rolling a 2 would also be 1/6 times 90, and so forth. Since in this case, all probabilities are equal, the expected counts are going to be equal for all of them. And lastly, it's calculate the chi-squared test statistic. So you could use that formula. Remember, it's observed minus expected divided by observed minus expected squared divided by expected, and then add them all up. So here we go. The probability of getting a 1, well, the observed or what actually it came out was 12 minus 15. 15 is our expected value. So 12 minus 15 squared divided by the expected value, 15. Okay. And you can add them up, and we would get our chi-squared of 14.41. I want us to look at these numbers a little bit. We got 1/6 or 0.6, 11.27, 0.6, 0.25, 1.67, and 0. So out of the expected values, right, the smaller this number is, the closer it is to what actually should happen, right? 0.6, that's only in this case, it was only off by 3 from what we'd expect, right? This one's only off by 3. This one's only off by 2. This one's off by 5. This one's off by nothing. But here, where is all the difference from? All that difference got put into the second category, 28 minus 15, and gave us a pretty large number. So our chi-squared really got a large number from this one big difference. All right. The next subsection is the chi-squared distribution and p-values. We use software to simulate taking 1,000 random samples of size 60 from the population distribution of M&Ms given by Marsing. Here are the values of the chi-squared test statistic for these 1,000 samples. So if you take a basically to summarize this, we are building what would become a sampling distribution. Now, a sampling distribution is every possible sample of 60 M&Ms. Here, we're just saying we're going to take a really large number in uh, our simulation, and we're going to take 1,000 of them. Okay. Um, and this is the result of it. So there's this thing that says larger values of chi squared give more convincing evidence against HO and in favor of HA. Remember, in a sampling distribution, each dot is one sample. So this is one sample, one sample, one sample, one sample, one sample, 1, 2, 1, 2, 1, 1, 2, 1, 2, 3, and so forth. Each dot is a sample. Okay. Now, what is the dot representing? Well, this x value, like it says, is a simulated chi-squared test. So right here, this would mean that from that sample, chi-squared equaled about 21. All right. This dot means that chi-squared equals about 17. All right. So when it says the larger the chi-squared number is, the more evidence against H naught and in favor of HA, because if you have a dot way far over here, the probability of it happening from here out of chance is very, very small. If I got some number here, well, by chance, that means it could have been anything in here. So it's pretty likely to happen. So the larger my chi-squared is, the more evidence against HA and in favor, or more evidence against HO and in favor of HA. And I kind of just wrote that in. The larger the chi-square value is, the less likely it's going to occur because I'm going to be way out in this right tail. Right? So for us, in 89 samples, I think our chi-squared value we got from before was 9.8. So in 87 out of the 1,000 simulated samples, the value of 9.8 that occurred in this class is 87 out of 1,000. So my dot or my of this sampling distribution would occur right around here. Right? And the probability of getting that or more extreme would be anything to the right. And the probability of getting something like that is, well, there's in our sample or in our simulation, 87 out of 1,000, which is 0.087. Okay. A chi-square distribution is defined by a density curve that takes only non-negative values and is skewed to the right. A particular chi-square distribution is specified by its degrees of freedom. So this is very similar to a normal distribution or a t distribution that we've talked about. They're both density curves, right? It's the area underneath them is equal to 1, and the probability is the accumulation probability from left to right. Okay. The difference between chi-squared and normal slash t distributions is that this is skewed to the right. Okay. Normal distributions are defined by its mean and standard deviation. T distributions are defined by its mean, standard deviations, and degrees of freedom. Here, chi-squared distributions are specified just by the degrees of freedom. That's what makes a chi-squared distribution special, is what the degrees of freedom are. So looking at it right off the bat, a chi-squared distribution with degrees of freedom of 1 is this blue curve. And it doesn't really make sense because, well, you very rarely will use this chi-squared distribution with the degrees of freedom of 1. The distribution of 4 looks a lot more like a chi-square distribution does, and then even as and you can see 8 here as well. But usually it's this thing, you have a mode to the left and then a long right tail to show that it's skewed to the right. Okay. The degrees of freedom is a number of categories minus 1 here. So in this, if there's a degrees of freedom of 4, that means there's 5 categories. Here there's 9 categories. All right. So it says the first thing to note, and these things are not required to memorize, but they might make some multiple choice questions a little bit easier to use. And there are also just some interesting facts that might be applicable as you get farther along in your statistics learning. But as the degrees of freedom increases, the density curve becomes less skewed. And you can see that right away from 4 to 8. 4, I had this large peak, and then I soon level out to the extremes. In degrees of freedom 8, much less subtle peak up and a much more gradual decline. Right. And I'd expect more and more of these, like 9 and 10, to be kind of here, boom, and then kind of lay out to the tail. The second bullet point is really interesting. The mean of a particular chi-square distribution is equal to its degrees of freedom. So you can see that here, degrees of freedom 4. Um, the mean would be right here at 4 as well. For 8, the mean would be at 8. And you can see that, um, well, it's kind of to remind you of the mean and median, right? Mean is that expected number. The median is where 50% of the data is. Um, so remember, and also you know that mean, what we're talking about here, mean is not resistant. So it gets pulled towards the outliers. So it's not surprising that our mean is pulled towards the right a little bit um, to be here. So knowing all this, I'd expect my median to be farther to the left a little bit. Um, but that's just a little bit of a review. But it's just something interesting. The mean of a particular chi-square distribution is equal to the degrees of freedom. Another interesting thing is for degrees of freedom bigger than 2, the mode or the peak of a chi-squared density curve is at df2. And you can see that very clearly visually. Degrees of freedom is 4, so the mode is at 2, or the top peak is at 2. And you can see that as well. Same thing with 8, it would be right at 6. So, like I said, things you don't have to memorize, but um, they are can be useful and very interesting. So back to our M&Ms. There's 6 categories. So our degrees of freedom is 5. The p-val is the probability of getting a chi-squared value of as large or larger than 9.8, given that HO is true. And so our chi-squared, we would have a distribution of df of 5. So every chi-squared distribution with degrees of freedom of 5 looks the exact same, like this. The mode's at 3. Um, the mean is at 5. Right, so right here, boom. And now the question is just, what's the probability of getting a chi-squared value of 9.8 or higher? Based on our table, we see that it's between 0.1 and 0.05. We want to use our calculator. I'll show you on here. We'll go on. Maybe, okay, there we go. No. Test, calc. Hold up. Distribution. You could see that I am coming back from spring break like all of you. But chi-squared CDF, and then you're going to put your chi-squared value, 9.8. A very large number to the right. We'll use 10,000 here, or maybe even 100,000. And then our degrees of freedom, which is 5. And I get 0.811. Okay, so same thing as our normal CDF works. It's left bound, right bound degrees of freedom. This is really more like a T distribution, left bound, right bound degrees of freedom. We did take a chapter off, right, from all this hypothesis testing, but this is a good caution. Failing to reject HO does not mean that the null hypothesis is true. Okay, so just remember everything we talked about with hypotheses apply again. We either reject H naught or we fail to reject H naught, and we go from there. So if we reject H naught, we have statistical evidence against H naught and in favor of HA. But if we fail to reject H naught, that does not mean that H naught, the null hypothesis, is true. It just means that we don't have evidence to say it's not true. Okay, that's the only thing we can do. And we go back to our little courtroom situation where you're never proven innocent, you are found not guilty. Same thing here. You don't know if the null hypothesis is true or not. You just know it is not false. So going back to that secondary example we talked about with the dies, we have our expected counts and our observed counts. Our degrees of freedom is 5, so it would actually be the same chi-squared distribution as the last one. Here, though, our chi-squared value is a little bit different. It's 14.41. So using just our calculator, well, if 9.8 gave us a 0.08, if I'm farther to the right, I'm going to have even less probability. So this value is going to be even smaller, and it turns out to be 0.0132. So even smaller. Right? So all this was used to build up to actually put the whole testing together. Okay, so we're going to do a whole test or talk about a whole test here. So it's very similar, right? Our state, we've done that. It was a hypothesis or slightly different. Now you also want to state what your alpha value is for your conditions, right? Um, Again, you always state the name of the test. So chi-squared test for goodness of fit. Now our conditions, the data comes from a random sample of the population of interest, and 10% when sampling without replacement, and is less than 10%. So those two conditions are very similar. Now the large counts is what's different. It's just that all expected counts are at least 5. And you might say, why 5? The same idea. Why our large counts for a normal distribution is greater than 30, where our n is greater than 30. And then for the proportions, where n times p and then times 1 minus p are both greater than 10. Now I'm worried I'm getting that wrong, so I am Googling it really quick. Yeah. So n times p and n times 1 minus p would have to be greater than 10. Here, it just means that all expected counts have to be at least 5 to pass our large condition. This is a really good exam tip. Remember to observe the expected counts, not the observed counts. Okay, what we'd expect to happen. And they say to make sure to write and label the expected counts in your paper, or you won't receive credit. So the same thing, you couldn't just say my sample size is larger than 30. You had to actually say n is bigger than 30. Here, you'd have to say each expected count is at least 5. This is just a little table. You could read it. So you can pause and read it. But let's carry out a test with this new example. All right. Um, so in this book, Outliers by Malcolm Gladwell, pretty good book. I'd recommend it. It's very interesting. But he suggests that a hockey player's birth month has a big influence on his chances to make it into the highest level of the game. Specifically, because January 1st is a cutoff date for youth leagues in Canada, where many national or NHL players come from, both players in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time and more coaching, and a better chance of being successful. To see if birth date is related to success, um, judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent season were selected, and the birth dates were recorded. The one-way table summarizes the data on birthdays from these 80 players. So they broke it up into 4 categories: January to March, April to June, June to September, October to December. Okay. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed across the four quarters of the year? So right at the bat, my state phase, right, of the four-step process, the H naught, the birthdays of all NHL players are uniformly distributed across the four quarters of the year. Or like we would say, we'd expect there to be 25% in each quarter. All right. HA, on the other hand, is the birthdays of the NHL players are not uniformly distributed across the four quarters of the league. So there's some difference between them, or they're not all equally likely to occur. And we'll use alpha at 0.05. Make sure you state alpha before you do any test for any test. The plan, we're going to do a chi-squared test for goodness of fit. The three conditions random. The data comes from a random sample of NHL players. Good there. 10%. We must assume that 80 is less than 10% of all NHL players, which is probably a pretty safe assumption. And then large counts. All expected counts are greater than 5. Well, if there's 80 people in the survey and we expect all of them to be equal, that means, and there's 4 categories, the probability of getting each category is 0.25. So the expected count for each one is we'd expect there to be 20 people born in each quarter of the month. And 20 is certainly larger than 5, so we are good there. The do phase, now we actually have to calculate chi-squared, the degrees of freedom, and our p-val. So to do the chi-squared, 32 minus 20 squared divided by 20. Same thing, same thing, same thing. This will be very similar to when you're doing binomial distribution. You have to do at least first, second, plus at the top, plus the last term. I would highly suggest just writing it all out. It's not going to save that much time to only do 3 instead of 4, or even 3 instead of 5 or 6. It's not going to be that much. You can still just plug into your calculator to get the number, but this is a really good setup. Okay. Or my degrees of freedom is the number of categories, which is 4 minus 1. So our degrees of freedom is 3. And then I'd use my calculator. So I can come here, second distribution, chi-squared, CDF, 11.2, comma, a very large number for our right bound. Ooh. Comma, 3.011. All right. And then we finish up with the conclude. And it's going to be very similar to before, but because our p-val of 0.011 is less than alpha, which is 0.05, we reject H naught. We have convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. All right. If you want to do this in your test, in your calculator, let's go into the stat, edit. My lists are very clunky, but that's okay. You want to put your expected in one column and your observed in the other. And I'm going to do observed minus expected. So observed in the first category. So 32, 20, 16, 12, and L2, my expected are all the same. So make sure, I've done this mistake before, where I put the probability here, not the expected numbers. Make sure you put the expected counts. After you have the list here, you're going to go into second distribution. Scroll down to chi-squared. Oh, not distribution is how you get the distributions. I want the test. So how I got there was stat over to test, and now I'm going to look for chi-squared, GOF for goodness of fit. Chi-squared test, 2 sample F test, linear regression test. I think mine's a little old, so we're going to do chi-squared test. Let's see if I can actually do this. Okay, interesting. So I don't have the same. So most of you will have this calculator where you can do observed L1, L2, degrees of freedom is 3, and then calculate, and you should get this out. I have a feeling I might have to put these in matrices for my calculator 'cause it's older. So give me a second. All right, I'm not trying to do it on the old calculator, but the new calculator, you should be able to do it this way. Um, you get the observed, the expected, and then go from there. And the nice part is they actually do tell you what each one of those values were. So this would be 7.2 is how would be 32 minus 20 squared divided by 20. And then this zero would also be 20 minus 20 squared divided by 20 and so forth. So it does tell you the values of there as well, which is kind of nice. So another AP exam tip, you can use your calculator to carry out the mechanics of a significance test, like always, but there's a risk involved. If you just give the calculator answer with no work and one or more of your values is incorrect, you will likely get no credit for the do step. So we recommend writing out the first few terms of the word calculation followed by dot dot dot. This approach might help you earn partial credit if you enter a number incorrectly. And then be sure to name the procedure, here chi-squared test for goodness of fit, and to report the test statistic, degrees of freedom, and p-val. These final three things are like the most important to do. I would highly encourage you to show your work, but if you don't have these three numbers on, then you're not going to get full credit guaranteed. All right. So the last thing is for the follow-up is that if your evidence is statistically significant, you could do a follow-up analysis. And basically that means is, well, where is it different? Okay. For example, in regular hypothesis testing, we didn't talk about it this way, but the follow-up for a hypothesis testing might be a confidence interval. Because if you found evidence that, hey, this does differ, then you might want to do a confidence interval to see, hey, where does it differ? Give me possible values of my mu that could actually exist. Here, if I do get statistically significant evidence, I might want to give um, a list of where. Um, so, if the sample data led to a statistically significant result, we can conclude that our variable has a distribution different from the one stated. To investigate how the distribution is different, start by identifying the categories that contribute the most to the chi-squared statistic. So, looking here, the things that um, influence the chi-squared statistic is obviously observed minus expected squared divided by expected. You add these numbers up. So we talked about this a little bit before, but specifically, hey, 7.2 and 3.2 are the numbers that really do add a lot to this chi-squared number. So that might be where some information is. Well, like, hey, look, in October, December, there's fewer than normal, and January through March is more than normal, so quite a bit more than what you'd expect to happen. Um, And so that's just kind of where you could do a follow up, like really seeing what the data is telling you. Where is this difference coming from? Specifically, in like what categories might be influencing the difference. All right. And then there are your um, learning targets from today. All right.